Lecture 5.5, Index of Refraction and its Frequency Dependence. There are three important behaviors of light that cannot be explained with the ray model of light. One needs the ray model light. One needs the wave model to do this. The first and most important is dispersion. Dispersion states here that the index of refraction is frequency dependent. In other words, the index is a frequency of angular frequency. So the index depends on one, of course, the material type. The type of medium, that's a material thing. And as I just stated, it depends on the frequency of incident light. So, for example, if n, the index of refraction, is a constant, the only way this could be true is that the incident light is monochromatic. Monochromatic means that it's of a single frequency. The problem is that's not what you typically get on light. So incident light in general is not monochromatic, but chromatic. So that means that you have multiple frequencies being emitted. Therefore, the index is dependent on the frequency. So, for example, here's what you're seeing here. Let me show you a thing here. White light is composed of the visible spectrum. So in equal amounts, you get the acronym Roy G. Biv. That was actually come up by Newton, which is red, orange, yellow, green, blue, indigo, and violet. So that means here, because there are multiple frequencies, because white light has multiple frequencies, its index changes. So here's what you find. If I have a higher frequency, that means I have a shorter wavelength. But if I have a shorter wavelength, it sees smaller electrons better, which then implies more interaction and therefore a higher index. So let me move this a little bit more to the middle. Okay, so now here we go. So I think I copied this. Let me see if I got it. Uh-oh, I may not be able to copy this. I have a table here. Okay, there's one table here. And when you look at this table, what is it that you see here? For this case here, this medium, this is the index of water, which is 1.33. And you could see here as the frequency changes or the wavelength changes, the index of refraction changes. So as you move, you could see here, as we're going down this direction here, you're seeing that the index varies with frequency. The important numbers that we should look at, around 650, it's about red, and at 450, this is violet. So right here, this is the visible spectrum. So when you look at a prism, for example, let me go copy the prism. So if I come in here and I paste this guy, here's a prism. You could see how it takes white light. And what you're finding here is that there is a separation of colors because the index changes with frequency and refracts different colors at different angles. That's why the prism is the way it is. It's because of the index of refraction is changing. Now, This one is a pretty challenging one. Okay, here's another one that's important. Frequency of a wave does not change when light crosses an optical boundary. And you know what? There's a lot of mistakes here. And I would say that there's a misconception is that many claim light is wavelength dependent. Okay? Light is wavelength dependent. And what I'm saying is it is not wavelength dependent. It depends on wavelength. Okay? It depends on wavelength. What's fundamental is conservation of energy. But energy is proportional to frequency. Okay? So remember, what's fundamental is energy. But energy is frequency dependent. So what this is telling me here is that conservation of energy then implies here that the incident frequency is then the incident frequency is also then the frequency of the refractive inside the refractive index. That is really, really important. So let me give you an example here. If you shine a red laser into water, its wavelength changes. But if its wavelength changes, according to some people, they'll say, hey, the color has changed. Guess what? That's not true. You can take one of these inexpensive lasers and shine it in the water yourself. What you're going to see here, if you shine a red laser from air into water, it's still red. It is not dependent on wavelengths. So what conservation of energy says here, it says that the number, okay, so the number of waves entering a medium must equal the number of waves exiting a medium. That has to be the case. Otherwise, conservation of energy would be violated. So when I look at a medium here, let's say that this is my boundary right here. And so what you're seeing here is that I'm looking at two different mediums. So in other words, I have medium 1, I have medium 2. So when I look at my waves are coming, and the number of waves coming in is also the number of waves coming out of the boundary. That's what it says. The number of waves entering a medium is the number of waves exiting. And what we'll see here later on, the only way to destroy waves, and note that there's quotes because it's more complicated than that, is through something called destructive interference. But even then, it really, really does change. So now, here we go. I've already said this, but we should say it again because it's a misconception. Frequency does not change when crossing an optical boundary. Yeah, you could see it online. Textbooks don't say that because they know better. But online, you'll hear people say, oh, it's wavelength dependent. So therefore, if I shine a laser, it should change color when it's in the water. That's not true. So now there are consequences to this. There are consequences to this restriction. So let's look at that. So if the frequency is constant, right? If the frequency across a boundary is constant, then regardless of what happens when you cross a boundary, I'm going to have to then say that according to the definition, that then the apparent speed divided by the wavelength must equal, no matter how many boundaries you cross, that ratio of apparent speed and wavelength must be the same, right? This is the consequence of conservation of energy. So what does that mean here? So there's some pretty interesting consequences of this here. So now, suppose N2 is greater than N1. Then that implies, as we've already said, then V1 has to be greater than V2. We've already said that. If you have a higher index of refraction, light interacts more strongly with the charges in the medium, and therefore its apparent speed slows down. So then picture-wise, it goes like this. So that means that this here is the fast medium. This guy is the slow medium. So picture-wise, what do we draw? We say that the frequency, which is a constant, then says if I have a higher velocity or I have a slower apparent velocity, then the wavelengths have to change to keep that value constant. So when I look at a medium again, I think I had my medium up here. Let's see if I can steal this right here. Oh, I'm going to have to change this. So let me paste this in there. I was going to try to be faster. Let's see what I can do. So if I change this, here's what I'm going to see now. So this index right here is going to be higher. So then I have my blue index here, and I have my yellow index here. So what does this mean? If I have a lower index, what am I going to see here? I'm going to see that I have a longer wavelength and I have a higher wave speed. In the higher index, I'm going to have shorter waves. No. I just made a mistake. Okay. Did I do that right? I think I did that right. Yes, I did that right. And then I'm going to have a smaller apparent speed. So here's what it says here. So if I look at this thing, it has to be this way, following this condition. So if I now interpret this tells me here is that if I have a higher wave speed, then I have to have longer waves as well. But if I have a lower wave speed, then I have to have shorter waves. So what I'm going to do here is that I'm going to show you a video, and to set you up for the video, I have two images that I want to show you. So this is one video, and this was with the Sheave wave machine that we've talked about already. And what I want you to pay attention is the length of the rods. In this image, you're seeing here that these guys are longer rods. These guys have shorter rods. Now, since this is a wave machine, this is a system of coupled oscillators. So what you should expect then is that if I have long rods, I don't know if I'm going to have to adjust this. Let's try right here. So if I have longer rods, that means that they have more rotational mass. In other words, we can also say they have higher moment of inertia, so they have a higher rotational inertia. Guess what? They're harder to accelerate. And because they're harder to accelerate, they have to transfer energy slower, so therefore they have a slower wave speed. Which means here, then they must have shorter waves. That's what it says up here. If I have a lower wave speed, I have to have shorter waves. On the other hand, if I have shorter rods, I have less rotational mass. In other words, they're easier to accelerate. If they're easier to accelerate, I'm going to transfer energy faster, and therefore I'm going to have a faster wave speed. And as a consequence, I'm going to have a longer wave. Okay, so now let's look at the video of waves crossing two different mediums. Now, I've hacked this video, so I downloaded it and I edited it and I took his words out. So I'm going to silence him, but I want to definitely show you this because I think it's a great video. So I'm going to be talking through the video and stopping it quite a bit. So here we go. So here he is, and you could see here that the first wave machine that he has his hands on has longer rods. The second one has shorter rods. So now I want you to pay attention to the wave speed. Don't pay attention to the waves. You can see the wavelength as well, but pay attention to the wave speed. So then check this out. Here's his wave speed on the longer rods. Okay, now here's the shorter rods. Now pay attention to the wave speed. You could see it's much, much faster, just like we talked about. Now he's going to connect them. And it's really the second one that's most important. It sees it better, but it's super fast. So pay attention. See how quick that wave transferred? Did you see how long that wavelength was? The other direction's better. So, but this is very, very short. Here it goes. Oops. It's the next one. Look at that. Look how much shorter that wave is. That's what we want to look at right there. So that video with the Shiva wave machine really shows you what we've been talking about right here. So now if I look at this thing mathematically, what do we see here? So okay, let me get set up. Here we go. To derive this mathematically, when a wave crosses an optical boundary. By the way, it doesn't have to be optical. But since we're dealing with optical stuff, I should say that the frequency, as I've already said multiple times, does not change. So then, mathematically, we say if the frequency is a constant, and then what I'm going to do here is I'm going to say, I'm going to write down two values. What you're seeing here is that this value here is it's for the vacuum, where in the vacuum, the speed of light is c, and it has a wavelength of lambda naught. And in this situation, we have a medium whose apparent speed is smaller than the speed of light in vacuum, and its wavelength. And now what I'm going to do here is that I'm going to solve for lambda n. So if I do that, I'm going to get lambda n, lambda naught, and then I get the ratio of Vn times C here. But it turns out that Vn over C is 1 over the index of refraction, which then tells you that this is the wavelength in a medium. And you could see here that this is dependent, the wavelength in a medium is dependent on 1 over the index. which is exactly what we saw on the video. Why did we exactly see this? Because check this out. If I have a higher index, then we had smaller waves. So if I look at this, here's my wavelength in the vacuum. And if I have a higher index, let me make this larger, then the wavelength is then going to be smaller. However, if I have a lower index, then I'm going to have longer waves because this guy is tiny, so then it's going to make this wave here. So if I look at the boundary, here's what I'm seeing here. I'm going to have waves that are incident, and here I come. And as soon as I hit the boundary, then these waves here get much longer here. And in this case, this is index of refraction where this is N2, and then this index is N1. And you could see here that N1 is larger, but the wavelengths in this situation is small. In this situation, they're much longer.